Welcome. This video is going to talk about thermochemistry. Thermochemistry sounds kind of daunting, but thermo just means heat. So thermochemistry is really just looking at the change in heat during a chemical reaction or some physical processes like dissolving, boiling, freezing. So the heat change can be positive and heat is absorbed by the substance overall, and we call that endothermic. Or the heat change can be considered negative because heat is lost or released by the substance, and then we refer to it as an exothermic process. Some types of reactions or processes are always endothermic or exothermic. For example, combustion always releases heat, always exothermic. Neutralization reactions between an acid and base, always exothermic. Boiling and melting, you always have to put energy in to get something to boil or melt, so those are endothermic processes. Whereas freezing, you have to remove energy, so that's exothermic. Other types of reactions or processes can vary, like synthesis or dissolving can be either endothermic or exothermic. It depends on the substances involved. So when you're talking about a process or reaction, how do you decide if it's endothermic or exothermic? Well, you really need to be able to think about things as the system and its surroundings. And by system, we mean the container where the reaction or process is taking place. So it could be your test tube or your beaker. But the surroundings then is everything outside of that container. So let's look at some examples here. Decide if each of the following is an endothermic or exothermic process. So frying an egg, the fry pan and the egg would be considered my system, and heat is going into that fry pan and to that egg from the hot stove you have it on. So that is endothermic. On the other hand, if you're burning methane for a stove, and methane is just what we usually think of as natural gas. So if you have a natural gas stove and the methane is combusting or burning, in that case, that's my system and the heat is being released to the universe or to the fry pan around it. Now it's exothermic. A hot pack obviously feels hot, so it's releasing heat, exothermic. A cold pack must be absorbing heat, making it feel cooler, so it's endothermic. So when talking about thermochemistry, the other term that comes up is this idea of enthalpy. So enthalpy is really just a fancy word for the energy in a system or the heat in a system. So the total energy in a system actually depends on lots of factors, and some of them we still don't really understand, or at least don't know how to measure. So for most systems, chemists can't actually know the total energy. And that's what this idea of enthalpy is the total energy that a system contains. But for most systems, we can calculate the change in energy, which we calculated with calorimeters and specific heat as delta H. And so we can calculate that for a reaction or a process, and that's really what we're more interested in, is how much energy is released or how much energy is absorbed. So enthalpy is a word for expressing that, and it's a strange word, but it comes from the Latin meaning heat within. So it's actually a better description than just heat. So you can think of enthalpy and heat as being the same thing. So what we're really interested in then is the enthalpy of a reaction, which is just the change in heat during a reaction, or what we symbolized with delta H earlier. And again, delta H is expressed as a positive value for endothermic reactions because there's net energy in, and it's a negative value for exothermic reactions because there's net energy out. So I've got two equations here, and one of these is endothermic and one is exothermic. And what I've done is I've written the balanced equation, and I've just included the delta H value after the equation. And in the first one, since the delta H value is negative, that's my hint that it's releasing heat or is exothermic. And for the second equation, because the delta H value is positive, this is an endothermic reaction. And just a quick note here, if these reactions were reversed, if I had 2 Fe2O3 and it was becoming 4 Fe, so it's decomposing instead of synthesizing, and most reactions are reversible, then I can assume delta H would now be a positive 1625, and this would have to be an endothermic reaction. Another way to express it is to actually list the energy change as either a product or reactant. Since this first one lists it as a product, that means the heat is being released or produced. So again, it's considered exothermic. But when it's listed on the reactant side, then it's being put in or added, and it's endothermic. So two different ways to indicate if a reaction is endothermic or exothermic, and by putting the actual value. So this last slide has a couple of graphs here, and you notice in each graph you have reactants and products. In this one, the reactants are lower, the products are higher, whereas over here the reactants are higher and the products are lower. So what are these graphs showing? Well, in both cases, the x-axis is the progress of the reaction, or you can think of this as time, as the reaction progresses over time. And the y-axis is energy. So it's really showing us the changes in energy between the reactants and the products. So why is the energy changing? Well, remember, in order for a reaction to occur, there's 3 steps. There has to be bond breaking, and that occurs with the reactants. And then eventually there has to be bond making, and that results in product forming. And then the middle step up here is where the atoms recombine. The atoms form new combinations. And so everything goes perfect. The reactants bonds break apart, the atoms recombine into new combinations, new bonds form, and we end up with new products. Well, bond breaking always requires energy. That's why we see the energy increasing here during bond breaking. So bond breaking is always endothermic, requiring energy. Whereas during bond making, we see the energy decreasing, so bond making is always exothermic. So overall, a reaction is either going to take more energy to break the bonds, or it's going to take more energy to make the bonds. So in this top graph, it takes more energy to make the bonds. In fact, here's my difference right here between these two. It took that much more energy to break the bonds. So this is an endothermic reaction. And I can also tell it's endothermic because my products have more energy than my reactants did. I had to put more energy into it, and that energy is stored in the products. Whereas in the bottom graph, when I look, the bond breaking, I'm just going to abbreviate it BB, the bond breaking took less energy than the bond making. That means more energy was released than was put in. And if that's the case, if the products have less energy, they've lost energy, and this would be exothermic.